Hi, I'm Professor Kelly, and this is an introduction to Haskell, a language in the functional paradigm, for the course CSCI 308, Programming Language Design. The language Haskell is named after Haskell Brooks Curry, a famous American mathematician. In fact, Haskell Brooks Curry has three languages named after him: Haskell, Brooks, and Curry. The learning goals for this lecture are to be able to run Haskell, to implement comments, primitives, functions, and constants in Haskell, to distinguish between where and let statements in Haskell, and to explain variables, pattern matching, and type inference in Haskell, and to recognize Haskell's type classes. Here's Quicksort in Java. It's quite a long piece of code. Here's Quicksort in Haskell. It's 3 lines. In fact, it's basically just one line. The first line is just a declaration of the type. On the first line, we declare that we take a list of integers and return a list of integers. The second line is just the base case. An empty list results in an empty list. An empty list is already sorted. The magic happens on the third line. Here we split the list into a head and a tail, called pivot in list here. We then quick sort the part of the list that is greater than the pivot, and we quick sort the part of the list that is less than or equal to the pivot, and we concatenate the two lists that result with the pivot in the middle. Haskell belongs to the family tree of programming languages. Specifically, it belongs to the functional paradigm. Previously, we've talked about object-oriented languages, such as C++, Python, and Java, which are imperative languages. And we've talked about Prolog, which is a logical language, part of the declarative paradigm. A functional language is a bit closer to the kinds of programming languages you've seen before, but it's still part of the declarative paradigm, and so is more closely related to Prolog than other languages you've seen. So if object-oriented languages are Homo sapiens in the tree of life, and Prolog is something very unrelated to Homo sapiens, such as an octopus, then functional languages, such as Haskell, are something in between. So imperative languages describe a sequence of step-by-step instructions for the computer to execute. This is a lot like following a baking recipe, assembling IKEA furniture, or putting together a Lego structure by instruction. Imperative languages include C, C++, Java, Python, Bash, Perl, JavaScript, Fortran, just about every language you've seen. Whereas declarative languages describe a situation and what must be solved without describing how to solve it. Declarative languages include Prolog and Haskell is specifically inspired by mathematics. A core idea of the functional paradigm is you can essentially just take math in a specific format and run it as code. The functional paradigm uses lambda calculus and recursion, and includes languages such as Lisp, Haskell, and OCaml. It's good for translating from code to math or math to code for the purposes of proofs, for example, and it also has very powerful pattern matching, which allows it to have very concise functions, such as for quicksort. To run Haskell, you have a few options. You could use id1.com, or you can install it on your own computer, or you can log into the Linux server. If you're logging into the Linux server, you may have to type module load 208, and then GHCI to launch the Haskell interpreter. Inside the Haskell interpreter, you can use :L to load a file, :R to reload a file if you've made mistakes and wanted to change the file and want to reload the same file after, and :Q to quit. In Haskell, comments take a number of different forms. It depends on the type of Haskell you're using. If you have a Haskell file that ends in .hs, then block comments take the form of squiggly bracket dash, and inline comments take the form of dash dash. Warning, the type of dash matters, so if you try copying and pasting Haskell code, it's possible the type of dash might get changed on you, and that could cause Haskell to crash. The other type of Haskell file is a .lhs file. L stands for literate. LHS stands for literate Haskell. Like before, dash dash is for an inline comment. However, literate Haskell uses reverse comments. So to indicate a line of code, you use a chevron. Whereas text, you don't use anything to indicate that it's just a comment. It's important to note when using reverse commented Haskell, comment lines cannot touch code lines. Use empty lines to separate them, as shown in this example. Haskell has the usual collection of primitives you'd expect of a programming language. It has integers. It also has integer, which is unbounded integers of any size. It has floating point numbers. It has double for double precision floating point numbers. It has char for characters. It has bool for true and false. Here's a Haskell function. The function's name is foo. It takes two parameters, x and y. The parameter types are the first two types listed on the first line, integer and bool. The return type is int. That's the last type listed on the first line. Note that there's no return statement. That's because return statements are a feature of imperative programming. Imperative programs give step-by-step instructions on what the computer is supposed to do. Declarative programs do not do that. Functional paradigm programs are essentially just math. This function is equivalent to fxy, where equals x, where x is an element of integers and y is an element of true or false. You don't need return statements in math. You don't need a return statement in Haskell. Here's another example of a function. This is bar. It has the parameters q, w, and e, and each of those have the type integer, and it returns an integer. It's equivalent to a function b here that takes q, w, and e and calculates the product where q, w, and e are elements of integer. Some functions don't have any arguments. These are constants. Here we have pi. Returns a floating point number, and it returns specifically the floating point number for pi. To call a function, we don't actually use brackets. We just type foo space 3 space true, and that gets us our return value. These are called curried functions, named after Haskell Curry. Curried functions do not require brackets. In fact, if you try putting in brackets, Haskell will get confused. You'll get an error. Basically what this error says is that foo was expecting 2 arguments but only got 1. Haskell looks at foo brackets 3, true and thinks that foo is being handed 1 argument and that 1 argument is a tuple consisting of 3 and true. You can, however, put the brackets around the function like this. That works fine. In fact, this is how you nest functions. We can call foo and then in brackets foo3 true and then false. Foo3 true is the first argument. Haskell resolves the first argument and gets 3, and then passes 3 into foo along with false and gets 3 again. Haskell has the usual assortment of built-in operators: and, or, not, equals, not equals, less than, greater than, as well as multiplication, addition, division, and so on. Haskell uses pattern matching. What this means is you can have a function that has multiple definitions. Here, foo has 3 definitions: one for when the second argument is 0, one for when the first parameter is 3, and another case where it can take any value. A restriction on these definitions is they all have to be the same type. This is unlike languages such as Java. The underscore indicates that an argument or parameter is irrelevant for this definition. Haskell pattern matches to definitions going from top to bottom. First, Haskell will check to see if the second argument is 0. If it is, it'll use the first definition. Then, Haskell will check to see if the first argument is 3. If it is, it'll use the second definition. Lastly, it will use the third definition if the first 2 definitions don't pattern match. If no definition matches, Haskell throws an error. Consider, for example, this function bar. Bar doesn't have the third definition. What happens when we call bar of 6 and 2? 6 and 2 doesn't match either definition. We get an error. Conversely, if we call foo 6 and 2, it fails to match on the first and second definitions, but it matches on the third, multiplies 6 and 2, and gets 12. Let and where allow us to define variables inside of functions. Where allows us to use the variable first and define it later. For example, here we have a function foo that maps from an integer to an integer. The argument is called w, and the return value is x plus 2 times x minus 4, where x equals 3 plus 4 times 5 times w. We can use x before having to define it. Let in, conversely, we define first and use later. This accomplishes essentially the same thing. We let x equals 3 plus 4 times 5 times w, the same definition, and then afterwards define the return value for the function. Variables are actually constant, and declarative languages don't have changes in state. This is why it's totally fine to define later and use first. Time doesn't actually exist. Let's look at this Haskell code right here. We have a function called goodbye that maps from an integer to an integer. Goodbye is defined as x minus 2, where x is the parameter. We have another function here called hello. Hello x equals goodbye x. We haven't defined types for hello. That's actually okay. Haskell can infer the type. The type signature at the top of function is actually optional. We can use :t to view the inferred type. We see that Haskell has correctly inferred that hello is a function that takes an integer and returns an integer. Let's consider another situation. Suppose we have the function identity x equals x. What's the type? Identity p to p. What does that mean? Well, p is a type variable. P has any type. Identity will take one parameter of any type, and it returns a value of the same type as the parameter it was given. Let's consider a more complex example. We'll take the type of foo. We have foo, equality p, number p, P to P to P. What does that mean? Haskell has inferred a type for foo. Equality A, number A, says that foo is defined for all types P where P is a number and P can be compared for equality. P to P to P says foo takes two parameters of type P and returns one P. This means that P could be an int, integer, float, or double. Foo will work for any of these types. To infer types, Haskell uses type classes. Equality is one of those classes. Equality is all types that can be compared for equality. This is all primitive types and some constructed types. There's also number, which includes int, integer, float, and double. Ordinal is a type class of values that can be ranked using less than, greater than, less than or equal to, greater than equal to, and whatever. This includes numbers, characters, but not booleans. Show is a type class for types that have a defined print function. This is a bit like toString in Java or underscore string underscore in Python. There are more type classes than this, but these are the ones you're likely to encounter. We've learned how to run Haskell, implement comments and reverse comments, recognize Haskell primitives, create functions, and constants as functions that don't take any parameters. Variables in Haskell never change. And pattern matching occurs top to bottom using the first definition that works. When you don't declare a type for a function, Haskell infers the least restrictive type and uses type classes to do so. And that's an introduction to Haskell.